got it? All right. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Pray that you just be with us today. Help me to be able to say things which are true and useful. In your name I pray, Lord Jesus. Amen. I have to pray that because the same can't be said for other classes I've tried to teach today. All right, so to start with, I want to tell you about a wonderful formula. I've already told you about this formula before, all right? But not quite in these terms. Well, yeah, for the moment. Don't worry, this shouldn't be that long. So I haven't fixed this yet, right? By the way, this is my 2015 notes. Obviously, I owe you some more notes. I will try to revise these so that they're over a field as been our custom. I will not keep it real if I have a chance to fix these notes for you. And but if you're eager to read this, you can look at my 2015 notes. It's chapter 8, all right? All I'm basically going to do to that chapter is change R's to F's. Otherwise, content-wise, it is verbatim what I will want you guys to look at. Of course, you can also read the appropriate chapter in Curtis, up to you. Now, so if we have an invertible n by n matrix, right, the formula for the inverse is given by this. 1 over the determinant of A, the adjoint of A transpose. Now, what's the adjoint of A? Yeah, exactly, you don't know. Fair enough. Let me show you. So the adjoint of A is defined to be the matrix. Let's see here how to do it. We talked about, remember we talked about Mij? We talked about Mij, the ijth cofactor, right? Well, this is the ijth, what is it? It's the determinant of, it's the determinant of A with, what is it, the ith row and jth column removed, right? Remember that? And then we said Cij was what? It was minus 1 to the I plus j Mij. Okay, so this adjoint of A is by definition the matrix of theCij's. So it's a standard notation for that Cij matrix that we looked at before. I had to talk about this with the expansion of the determinant about a row or column. Now, let me just make it a little bit more concrete for you guys. Let's look at a 2 by 2 matrix for just a second here. So A, B, C, D, all right? So in this case, let me just go ahead. M11 is what? It's the determinant of everything except for the first row and first column. It's determinant of D. What's M12? Delete the first row and the second column, C. Determinant of C, right, which is C. M21, determinant of B. M22, let's see here, determinant of what? Rather, A, right? These are the minors. Minors are subdeterminants of submatrices. And then, so what's this make C11 equal to? C11 is equal to D, C12 is equal to minus C, C21 is equal to minus B, and C22 is equal to A again. So in other words, the adjoint of A is equal to the matrix D minus C minus B and A. All right? So what was the formula we had for the 2 by 2 inverse? Remember that? It was 1 over AD minus BC, right, times what? We flip the diagonals. We put minuses on the off diagonal, right? Well, that's kind of, so this is like 1 over what? The determinant of A. See, that's not quite the adjoint, is it? But it's the transpose of the adjoint is what it is. It turns out that formula is general. That's also true for 3 by 3, 4 by 4, you name it, as long as the determinant of A is non-zero. Let me show you the proof of that. Oh, sorry. Okay, long enough. It'll come back in a second. Or you can get out your infrared goggles or whatever it is. All right, where did I put my laser? Oh, here it is, my laser. So the first proof I would suggest that we ignore. Second proof is more gooder. Haha, I said it. It doesn't make any sense. Then why'd you understand it? Haha. Take that, English people. AA inverse is equal to the identity, right? That's what you're trying to solve. If you're trying to find the formula for the inverse, you're trying to find columns that you can make into a matrix, right? N of them, and really what you're trying to do is let A inverse be like V1 through Vn, right? You're trying to separately solve these equations. AV1 equals to E1, AV2 equals to E2, AVn equals to En, right? You have these n equations to solve simultaneously to find the inverse. So, but we know Cramer's rule, right? So Cramer's rule gives us just a straight up formula to solve these. Like the jth component of V1 is what? We take we take A, all right, and we remove the what do? We remove the jth column of it, right? And we replace the jth column with what? With E1. All right. Well, if you look at that, that's actually the same as C1j, where that's the cofactor. So that's the thing. If you take the matrix, A, right, and you remove the jth column and replace it with E, what is it? What I say? E1, right? Then there's only like one non-zero entry in that jth column, and so what you'll have is the determinant of an n by n submatrix. If you look at that, you can see that it's exactly C1j. This is, in other words, it's minus 1 to the 1 plus j mij. So, and then if you don't see this right away, you could like write down the 3 by 3 case and try to convince yourself of it. If you're not seeing it, it's. I don't think I see it today, but I wouldn't take much from that. I don't see much today at the moment. So you apply Cramer's rule to deduce the jth component of the inverse. All right, so you can do this just as well for the ith column and get Cij over determinant of A. All right, so that's the, what is it? That's actually this I is what? It's actually a column index, right? So this is actually A inverse parentheses Ji. This is the jith component of the inverse. So this shows that the jith component of the inverse is Cij divided by determinant of A. So by definition of transpose, the inverse is the transpose of the adjoint divided by the determinant. This is very nice to know about because it gives us a formula for inverse, which is useful for theoretical purposes, if nothing else. Like, I used it last week when I was talking to some students about topology. Like, we wanted to argue that inversion of matrices was continuous. Well, I can give an argument there because the formula for the inverse is nothing more than a rational function of the components, and we know rational functions are continuous functions, so it follows that the inverse of a determinant is a continuous function. That's the kind of place where you actually use this formula, that sort of application. In terms of actual calculation of a matrix, don't do this, right? We go back, we use the thing we talked about before, quiz 1, right? You you tack the actual matrix onto the identity. Here is, for the sake of, just for kicks, here's C11, C12, C13, C21, C22, blah, 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 blah. Here's all of the cofactors for the 3 by 3 matrix, A, B, C, D. Well, it depends on how you read it. Where's the hand? I want the hand. How do I get the, I want to be able to, oh, whatever. So A, B, C, D, E, F, G, H, I. These are the cofactors. Behold them in all their glory. The adjoint is that. There's its transpose, rather. And so here's the formula for the 3 by 3 inverse. Oh, come on. Stupid. So, I mean, stop that. I tell you, I'm about to. There is that same thing I derived from just saying criteria for invertibility at the start of this discussion, right? And obviously, this is not something you want to remember, right? But it's fun to try it out. If you try for example, the matrix 3i, you get this, which gives you 1/3 I, which is totally unsurprising as an inverse, right? Anyway, so just let me share with you a couple applications of determinants while we got this out. One of my favorite applications of determinants is found in physics. If you have n electron wave functions, chi1 through chi n, what you can do is to find the wave function of like the whole system of these. You can put the determinant. You can look at the determinant of all the wave functions put like this. This function will be completely, I believe, anti-symmetric in the positions R1 through Rn. And anyway, it's known as a Slater determinant. It's a nice way of imposing the Pauli exclusion principle in a formula. Anyway, so you'll study that again when you take quantum mechanics here. Everyone here will make an A in quantum mechanics when they take it. It's good. But unfortunately, you will all also fail the course. Sorry. We don't have such a course, yes. OK, so this is the Vandermonde determinant. What you do, this is really cool. You put 1s in the first column, and you put x1, x2, x1, y1, x2, y2, and x and y, like this, all right? Properties of the determinant. What is this formula, first of all? Just like look at it, think about it. If x1, y1, and x2, y2 are given numbers, right? This is a formula which is linear in x and y, right? This is a formula which is linear in x and y and is based on the given numbers x1, x2, y1, y2. So it's a linear function in x and y, right? So its graph is a line. Which line is it? Check it out. If the row is repeated, what happens? The determinant 0, right? So in particular, from the very properties of the determinant, you can immediately see that if you put x equal to x2 and y equal to y2, solution. If you put x equal to x1 and y equal to y1, solution. So this is the equation for a line which goes through the point x1, y1, x2, y2. If you understand this trick, you can use determinants to create all kinds of formulas that build in data in this way. It's a sneaky trick, but I don't know what is this down here? I don't know what this was about. I forgot. I don't know. Oh, I'm deriving the stupid 2-point formula from a line from row reduction. Yay. OK. Another fun thing to do is you can create differential equations. Like if I have y prime, and y prime prime as variables, and if I want that to have the solution y1 and y2, if I do this and I set that equal to 0, automatically I get a second order differential equation which takes y1 and y2 as solutions. Now, if you just try to create a second order differential equation which takes two independent functions as solutions, you might find that somewhat challenging. But this is not. So determinants are awesome. And then, of course, there's just the more basic geometric thing, which is you can think about its significance to linear transformations. If I've got a linear transformation from R2 to R2, like this, it maps the origin to the origin, this to that, this to that, this to that. You can ask what's the significance of the determinant of the standard matrix. Well, here's a picture. We're starting with this rectangle. That's the transformed parallelogram, right? So this is an injective transformation. It maintains the dimension of the things it's forming images of. It takes something two-dimensional to something two-dimensional. That to me immediately says it's injective. Dimension's not lost in the image. But the area of R you can calculate is 3. 1 up, 3 over. This has area, well, the height of this parallelogram is what? It's 1. And what's its, we got 6 is its base, right? So that has also area 6. What's the relation of these two? The determinant of R is exactly, its determinant of T is actually 2 if you look at it. So the determinant of a linear transformations matrix tells you the scale factor with which it's multiplying area, or more generally volume. So for example, if the transformation is not injective, right? If it doesn't maintain, if there's more than 0 in the kernel, right, then that would indicate, we're talking about transformation from, say, Rn to Rn, I would immediately be able to understand, I would know immediately the kernel was non-zero. That means that what? The column space is not n-dimensional. I mean, the columns are linearly dependent. This is not an invertible transformation, right? But in terms of the determinant of such a transformation would be 0. So if the function's not, if the transformation's not injective, the determinant's 0. And so what happens is it may squash the area from something non-zero to something 0, generally speaking. It's still possible you could maintain, well, I'll shut up. And then that's all I got for here. No. Oh, I guess I should have asked if there was a question before I did that. Oops. Are there any questions? Don't worry, your test is not graded. I haven't even looked at it. I mean, I looked at it. I thought I should grade this. And then I had 30,000 other things to do. So, sorry about that. So I think it's very neat that even looking at the 2x2 case reveals the general formula. I stopped it with my mind. So, all right, so there is something I should mention, just the problem of linear transformations and coordinate change, all right? And similarity, let's say. Okay, so I defined the determinant of a matrix in what I've shown you so far, right? But in fact, I was talking also about the determinant of a linear transformation in my last example. How do you define the determinant of a linear transformation? So here's the deal. If T is an element of the linear transformations from V to V, all right, where V is a vector space over a field F, then here's the interesting thing. The determinant of the matrix of T with respect to the beta basis is equal to the determinant of the matrix of T with respect to the gamma basis for any pair of bases beta and gamma for V. Why is that? What's the relation between the matrix of a linear transformation and, with respect to one basis and another for the same vector space? Do you guys remember? We had a theorem before which said what? There exists P invertible such that what? T gamma gamma is P inverse T beta beta P. When two matrices are related in this way, they're said to be similar. So the matrix of a linear transformation with respect to two different choices of bases, these are similar matrices. So but this theorem we proved before in our coordinate change day, okay? So the proof of this proposition up here, right? What's the proof of the proposition? Well, proof the determinant of T gamma gamma is what? It's the determinant of P inverse T beta beta P. What are the properties of the determinant? The most precious of them is that it's the product. So we can break this up into the determinant of P inverse times the determinant of T beta beta times the determinant of P. But what is the product of a determinant and its inverse? Let me just say that these cancel by a lemma, okay? Doing a little time travel right there. I haven't proved that lemma yet. You guys have no problem with time travel, right? Fine. So setting aside this current acausality of this argument, we have what? So it doesn't matter what choice of basis you make for the vector space. The determinant of the linear transformations matrix is the same. Let me prove that lemma before we go on. How would I prove that lemma? So here it is. If A inverse is equal to I, then the determinant of A inverse is equal to 1 over the determinant of A. That's like, how do you prove that? So you're given A inverse is equal to I, right? Take the determinant. We get the determinant of A inverse, which is equal to what? Determinant of I, but that implies what? That implies the determinant of A times the determinant of A inverse is equal to I. By the property of determinants, the determinant of a product is a product of the determinants. I did not prove that for you, but the proof in gory detail is in my notes. You can read it and appreciate it. It involves elementary matrices. It's a technical thing. It's by far the most non-trivial identity I've stated this semester, that the determinant of a product is a product of the determinants. And there it is. Just divide, right? Can the determinant of A inverse be 0? Of course not, right? Because, I, come on, don't make it, guys, you gotta stop me. I, come on. I, golly. What's the determinant of the identity matrix? 1. Yes. You were not lost. You should have spoken up. You were right. I was wrong. You should have said something, some of you. You're like, I'm still 15 seconds behind where you are. Chillax. I don't acknowledge that as a word. Sorry. So therefore, the determinant of A inverse is 1 over the determinant of A. Lemma completed. Closed time loop maintained. Phew. Hawkins can breathe a sigh of relief. All right. So we have this. This is really nice, right? Because this means I can make a definition. And here's the definition. And this definition is unambiguous despite of its ambiguity. If T is an element of the linear transformations from V to V, with the dimension of V being less than infinity, all right, then the determinant of T is equal to, it's equal to the determinant of the matrix of T with respect to beta beta for beta a basis of V. And you see, it doesn't matter. the ambiguity of that choice, the determinant's still well defined. Because different choices I make, I still get the same number, determinant of t. Is there anything else you can define for a linear transformation like this? The other thing that's important that you can define in this way is the trace. Observe the trace of t gamma gamma is equal to the trace of p inverse t beta beta. P, like that. But you had a homework problem, right? What did I do? Oh, is this hiccups? Okay. I'll accept it. It's scary? Okay. So a property of the trace is that it is, I can do this. This is the trace of p inverse t beta beta, which, by the way, is the trace of t beta beta. So you see, I can also define trace for a linear transformation in the same way I did here. I mean, this and the trace of t, trace of a linear transformation t is equal to the trace of t beta beta. Okay? Same song and dance. It's reasonable because of what I wrote below there, right? Any questions about this? No. Okay. So, ideally, I wanted to give you guys a lecture today on what I just did, but then also polynomials and the theory of polynomials. But I'm just not ready. So I'm going to go on to Chapter 7, and I will just admit, what I'm going to try to do is give you a big picture of where we're going, and basically take a tour ahead in Chapter 7 where we're going. Hopefully come Monday I'll come back and prove or state technical details which are necessary. If you want something to work on for this course, I would recommend you read Chapter 6 in Chapter 6. Yeah, Chapter 6 in Curtis. I'm working on putting together a homework for you guys for next Friday. Hopefully it will be short. But that's one of the things I'd like you to do, just read Chapter 6. So Monday's lecture makes more sense. The homework should be out soon. If it's not out soon enough, then I will make it due after break, okay? So what is soon enough, I have not defined yet, but I'll know it when I feel it. So if you're bad people, you can hope that I get sick, and so I won't be able to make the homework. That seems like a real possibility. I feel a little bit off right now. But you guys are good people, so you want homework, right? No? Relatively short, yes. You have midterms next week or after break? Ah, I see. Well, I will keep that in mind. All right, so with that, I'm going to begin the theory of a single linear transformation on a vector space V over a field F. So this whole, I don't know how many lectures, for a few lectures, maybe 3 or 4, I forget exactly how many I've allotted, but for a few, we're just going to be studying what can we say if you have a linear transformation T, right, and it goes from V to V, linear. Like, what's the structure of such a transformation, all right? Okay. So we already have some results for this already. Like, what do we already know about such a transformation? What's probably the biggest thing we know? A few things. Things we already know. Let's kind of make a list. Let's see, what do we already know? We already know that the kernel of T is a subspace of V, right? We know that. Proved that before. How about the range of T? Well, or sometimes we'll call this T of V, and I'll call it the image of T, right? This is also what? A subspace of V, right? Anything else we know? I mean, I guess those are kind of basic things we know. Here's a slightly more technical thing we know. We know that the determinant of t is not equal to 0 if and only if t is invertible, right? Can you add to this equivalence? I can add a few things. What? If and only if t of v equals to what? V again, right? If and only if what? The kernel. Just 0, right? Anything else? I mean, I had a list of about 10 statements that were made at the level of matrix notation, right? But I think these are kind of the 4 big ideas. Non-zero determinant, existence of an inverse, surjective, injective, right? Because in the case that the domain and the codomain are the same vector space, rank nullity is especially useful, right? So we have that the dimension of v, right, is equal to what? The dimension of the kernel of t, right, plus the dimension of the range of t. In other words, I usually use an n for this, so n is equal to the nullity of t plus the rank of t. So, like, what's the proof that injective implies surjective? So if right, t is going from v to v, and the kernel of t is equal to 0, then what we have n is equal to the what? 0, well, let me just write out nullity of t, right, plus the rank of t. But what's the nullity of t is 0, right? Because that's the dimension of the kernel, which is 0, right? So what does it say about the rank of t? Is equal to n. In other words, the dimension of the range of t is equal to the dimension of v itself. In other words, it's what? It's a surjection. So this is such a special context. When we're looking at a linear transformation from a vector space to itself, it's so very special, right? Injectivity, if and only if surjectivity, right? Now we can start asking more adventurous questions like, how about this? Here's a question. Is v equal to the kernel of t plus the range of t? What do you guys think? True or false? I mean, we have what? We have the dimension of this plus the dimension of that is n, right? So it must be that this is true, right? It's a trap. When would that be true? I mean, what would... Certainly, the kernel of t, right, plus the range of t is what? This is a subspace of v, right? Because the sum of subspaces is, again, a subspace. What's the relation between the sum and the intersection of the subspaces as well as the subspaces? Remember that thing we proved? What was the result? Was the dimension of, how did it go? S1, was it S1 plus S2? How's it go? I can't remember. Minus, let me draw a picture. S1, S2. So like the whole thing, I guess, would be S1 plus S2. And so that minus, how'd it go? I can't remember. So I'm sorry, dimension of S1 plus the dimension of S2. How does it go? I'm literally too stupid to remember at the moment. Help me out. Minus the dimension of the intersection is equal to? Let's see here.
I'm pretty sure it's rewritten with the intersection being like on the other side, but yeah.
That's a way we could express it. Is this true? Well, if you forget, you can always check stuff, right? And so a good way to check it is something with a non-trivial intersection. So for example, let this be S1, let this one be S2. In other words, S2 is like the span of E1 and E3. S1 is the span of E1 and E2, right? S1 intersect S2 is what? It's just the line. So it's the span of E1, the x-axis. And S1 plus S2 is what? Everything. Let me check my formula. So I got 2 plus 2 minus 1 equals 3. Okay, I start to believe. I did prove it in the notes in gory, stupid detail, but anyway. All right, so let's apply that to the current question. What does that do for us? Think of this as being S1, right? Think of this as being S2. What do we have? So I guess I get what? I get this gives me what? Dimension of the kernel plus the dimension of the range, right? By rank nullity, this is just the dimension of V again, right? So minus the dimension of the what? The intersection of the kernel and the range. Is equal to the dimension of the kernel plus the range, right? So when is it true that they're actually equal? What do you need for V to actually equal the sum of the kernel and the range? Right, we need the intersection of the range and the kernel is 0. All right. I'm just playing around at the moment. Did I put that on your test? No. I think I did put, I think I put this on your test, but not this. I had put that on your test, and then I think I undid it. Was it a good decision? Yeah, it was a good decision. All right. So, all right. So, I'm just exhibiting some of the tools we can use here, right? Again, our ultimate goal is to understand what's the structure of a linear transformation on T, right? So, we'd like to understand, like, when are two linear transformations sort of the same transformation, right? What does it make? When can we say? Let's see here. What do we want to mean by? Let's see. How about this? When would we say that T1 and T2 are the same transformation? Well, and I don't mean identically the same transformation. I don't mean that they're equal as functions, but I mean that, let me put some quotes on that. I want to try to explore that concept. Because, see, to classify linear transformations, we need to come up with some idea of like when are two the same or not, right? Let me submit to you this is a reasonable starting point. If, right, if you could find, if there exists a basis beta and gamma bases, right, for which, and maybe there's more linear, pure linear algebraic ways to come to this idea, but this is my current idea. There exist bases rather, plural, right? Beta and gamma, and of course for V, all right? And what if there existed bases, right? With respect to these particular bases, the matrix of T1, with respect to, say, the beta basis, was equal to the matrix of T2 with respect to the gamma basis. Wouldn't they essentially be the same transformation, just written with different coordinates? I mean, that means that in the beta coordinate system, T1 acts the same way as T2 acts in the gamma coordinate system, right? So I would argue that means that T1 and T2 are essentially the same transformation, just in disguise. What would that say then about these? What's the relation? If this is the case, what would you be able to do? Well, you could change this to the beta basis. I mean, we'll change that one to the gamma basis. How? In our notation, that would be P inverse T1, right? P. Oh, sorry. What am I doing? I forget which one I had on which side. Did I erase it all? It's somewhat immaterial. I mean, you can go either way. Let's just say, I've already written this. Let me stick with it. What's that? So I had it? Okay. So that was, but gamma gamma? I mean, let me just take a breath. P inverse T1 gamma gamma is equal to T2 gamma gamma. My point is I could change coordinates, right? I could look at the matrix of T1 with respect to the same basis by change of coordinates on that one, right? So this is just coordinate change. So in other words, what you see from this calculation is that, let me call this condition 1. So condition 1 is entirely equivalent to saying that there exists a basis gamma such that the matrix of T1 with respect to the gamma basis is similar to the matrix of T2 with respect to the gamma basis. In terms of your note-taking, you'd be safe to just write T1 sub gamma and T2 sub beta. I'm only writing gamma gamma and beta beta as to be consistent with my earlier notation. But in terms of redundancy of notation, it is certainly a redundant notation because it's always going to be beta beta and gamma gamma, because we are always going to be looking at, for a while in here, the case that we give the same basis to the domain and the codomain of the transformation we're studying. Okay? So check it out. We have now a new problem. A real question is, when are two matrices similar? When are two matrices? Yeah.
Your P inverse, should that be T sub beta beta? Lower one.
You have both gamma gamma.
P inverse T1 gamma gamma P equals T2 gamma gamma. That'd be T1 beta beta. From your above equation.
This here?
Yeah. P1 T beta beta.
But it's T1 and T2.
No. I am doing coordinate change on this to get to here. That's my point. Those are equal.
Oh, okay.
I'm changing from the beta coordinate system to the gamma coordinate system. And what I'm trying to say is two linear transformations actually have the same matrix in different coordinate systems if in a given coordinate system their matrices are similar. Two matrices two linear transformations have the same matrix in different choices of coordinate system if, in a given coordinate system, those two transformations have matrices which are similar. Two matrices are similar, like B is similar to A, if and only if there exists a P invertible such that B is equal to P inverse AP. Similarity of matrices is very nice. It's an equivalence relation on the space of matrices. Do you guys know what that means? So, as we're starting to think about this problem of classifying transformations, it's somehow related to the corresponding question for matrices of classifying when are two square matrices similar to one another. How do you decide that? Given two square matrices, how would you decide if there exists a P such that P inverse AP is equal to B? For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 1, 1, 1, 1, 1, 1, 1, 1. Are these similar? How do you know that there doesn't exist a P such that P inverse of the one times P on the other side gives you the other? How do you know that? I mean, you're right, but why? There are certain invariants of matrices. And so what I say is, so it's an equivalence relation, right? Let me be more specific about that. Oh, I don't think I have time to do that properly, so I won't. But just in words, you know, if equivalence of matrices, or rather similarity of matrices is an equivalence relation, what that means is given two matrices, all right, they're either similar to one another or they're not. And you can take the collection of all matrices which are similar to one another, and this forms an equivalence class. All right? Certain things about matrices are invariants of each equivalence class. For example, the determinant. We just proved that the determinant, I erased it, but earlier today we proved that the determinant of T beta beta was the same as the determinant of T gamma gamma, where they were related by a similarity transformation. It was P inverse T beta beta P or whatever, right? So the determinant is constant on equivalence class of similar matrices. So if two matrices have non-matching determinants, well, that's an easy one. Now you can easily see that the determinant of the right matrix is 0, right? But the determinant of this matrix, I think I worked it out before, or maybe I didn't, but you can calculate it. What is it? 1 times 45 minus 48 minus 2 times 36 minus 42 plus 3 times 32 minus 35. That's not equal to 0, okay? I hope it's not equal to 0. I'm pretty sure it's not equal to 0. So since their determinants are not equal, it stands to reason that they can't be similar, because similar matrices have equal determinants. It is 0. Dang it. 3, 1. 3, 2, 1. There. Ha. There. Take that. Ah. Okay. But this is a difficult question. When are two matrices similar? It turns out, if we study something called eigenvectors, if we study something called invariant subspaces of matrix, it's like one of the first things we'll do is we'll start looking at what if you take a vector x, right? And then you take a vector t of x, and then you take a vector t squared of x, and then t cubed of x, and so forth, right? And so forth and so on, right? If you look at the span of these, what do you have? T of x is again a vector in V. T of x is again a vector in V. T of x is again a vector in V. Taking a span of them, it's a subspace, right? And you can, this is a subspace of V. You can call this thing W. And it turns out that T of W is once more a subspace of W. It's a subspace of W again. So a subspace constructed in this way gives you what's called an invariant subspace. It doesn't go anywhere else when you act on with a T. Then if you construct a matrix, all right, if you construct a matrix for a linear transformation based on such an invariant subspace, if you have a basis which respects this thing, like suppose you have a basis beta, which is basically a basis for W, union with a basis for not W, okay? Then if you look at the matrix of T for such a thing, what you get is something really nice. You get the matrix of T restricted to W up in here, and you get zeros, and you get zeros, and you get stuff, if I remember right. I may have to. Well, anyway, that's where we're going, this kind of construction. We're eventually going to learn how we can take apart a matrix and look at it, basically its fundamental building block, its skeleton. This ultimately leads to what's called the Jordan form, which answers the question I posed today in all possible stupid cases. So anyway, I shut up. Thanks, guys. Read chapter 6. Don't sweat the complex stuff too much.